Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving here today, as it is every day, here in my virtual classroom. Step on aside as we dive into the Chapter 5 test and cumulative assessment in the Big Ideas Math Integrated Math 2 textbook, things regarding probability and statistics, and then the cumulative assessment, anything before that from chapters 1 through 4, including things on Chapter 5. Now, just a word of warning and caution, because of the multiple videos I've been recording in sequence and storing on my computer, I'm actually running out of computer space. So I think I have to get this one done within an hour 15. Normally I think I do, but you already see the time for how long this video is. My warning is basically I might go over problems a little quickly here in such a way that I might not teach them as much. This is the test portion. See what you know. Try and check it compared to what I have. And I'm just going to mostly try and do the problems, I guess. I can't say like, or you do it this way or that way. And there's some problems if I have to like build something, like we've been doing histograms and stuff, maybe I have to pause to build the histogram and then resume so that way it doesn't take up computer recording space. That being said, I'm going to go ahead and get started. There are two different sections here. You can download these things below in the description section, the test and the cumulative assessment. We'll start this with this page, numbers 1 through 14 on the chapter test. Number 1, or rather numbers 1 and 2, you roll a 6-sided die, find the probability of the event described, and explain your reasoning. The probability of rolling a number less than 5 on a die, you have 6 numbers to choose from, 1, 2, 3, 4, 5, 6, and the numbers that are less than 5 are 1 through 4, and there are 4 out of 6 that are possible there, which is 2/3. If you use a percentage version, that's around 66.7% approximately. So 2/3 or 66.7%. My reasoning is these are the 4 in the subset that are less than 5. Number 2, you roll a multiple of 3. Now, numbers that are a multiple of 3 among these sets are 3 and 6. That's 2 different numbers out of the 6 that you can choose. So 3 and 6 for number 2, probability multiple of 3. 2 out of 6 is 1/3, and 1/3 is around 33.3%. That's a fancy way of me writing that in that order. I'm really trying to rush on those two, and hopefully those felt okay. Numbers 3 through 6, we will evaluate the expression. So on number 3 and 4, we have permutations. We got 7 pick 2. 7 pick 2 is 7 factorial over 7 minus 2 factorial, which is 5 factorial. That's 7 times 6 times 5 factorial over 5 factorial. 7 times 6 is 42. 42 different ways that I can arrange 7 items into 2 slots, basically, is the way that's being said. Number 4, we have 8 pick 3. By the way, pick is just the word that I say for that. We're really referring to permutations. 8 permutations of 3. See, I like to say 8 pick 3. 8 factorial over 8 minus 3 factorial goes here. That's going to be 8 times 7 times 6. The times 5 factorial is canceled out on bottom. So I get to do basically 42 times 8, right? That's 336. 336 possible arrangements of that. Permutations are things where order matters, and that's all considered in its formula. Number 5, I want to make sure that answer's right. 42, I think so. Number 5, 6 choose 3. 6 is in reference to combination where order matters. Same kind of formulas you just saw above, only instead of just the 6 minus 3 factorial, there's also the r factorial in and of itself. So 3 factorial times 3 factorial. So 6 times 5 times 4 times 3 factorial. Let's get rid of that 3 factorial, and we've still got a 3 times 2 times 1. 6 over 3 is 2. 4 over 2 is 2. And you're left with 2 times 2 times 5, which is 20, over 1. So that will be 20. 6 choose 3 is 20. Number 6, we have 12 choose 7. That'll be 12 factorial over 7 factorial times 12 minus 7 factorial. 12 factorial over 7 factorial times 12 minus 7 factorial, which is 5 factorial. So the 7 factorial I can make go away if I just stop at 8 here. 9 times 8. 7 factorials be gone. And then here I have 5 times 4 times 3 times 2 times 1 as well. Let's do some reduction. Highest numbers first. 12 divided by 4 is 3. 10 divided by 5 is 2. 9 divided by 3 is 3. 8 divided by 2 is 4. So I have, oh boy, 9 times 4 is 36, times 2 is 72, times 11 is 792. I'm going to check 7. Let's see if I did that right. 792. This is a time where I should pause as I go to the calculator here. But I'm going to check. Bringing up my calculator. I didn't have it up. All right, so 12 choose 7. Yay! Okay, we got it. 792. All right, so that was doing it by hand. Listen, we could have done them all in the calculator, but I'm sure the whole point of the test is maybe you can't. Right? Maybe you can't. All right, number 8. You find the probability, A or B, that by using the equation P, A or B is A plus B minus A and B. Describe why it's necessary to subtract A and B when the events are overlapping, then describe why it's not necessary when they're disjoint. Yeah, so the whole idea of the A and B is, I mean, they kind of answer it in and of itself. When something overlaps, when events overlap, they are not mutually exclusive, meaning the one event occurring can mean another event occurs as well. When you add the probabilities, individual probabilities together, you are doubling up the overlapping values. You are doubling up the overlapping occurrences. Therefore, you must subtract one instance out. I feel like I could have just used that last sentence instead of the first one. I didn't really probably have to say the mutual exclusive part. I think that part's kind of implied. Now, when events are disjoint, there is no overlap. Therefore, there is no such instance where both events can occur at the same time. So there is nothing in excess to double. And therefore subtract. So the one that I often say is the heads tails case. If I flip and land on heads, then I'm not going to land on tails, right? Those are disjoint events. There's no probability of heads or heads and tails to subtract out from that, as there's no doubling up to be had. And that's number. Oh, I skipped number 7. Well, you're going to have to deal with that. I'll go back to number 7. That was number 8. So just check the timestamp stuff. That's how I always say check the timestamp stuff. I skipped it. Let's go back. All right, number 7. Sorry about that. Number 7, the odds in favor of an event are 2 to 9. What are the odds against the event? Well, odds in favor, 2 to 9. That means 2 in favor, 9 against. So odds against are 9 against, 2 in favor. 9 to 2. All right, there was number 7. Sorry for skipping it there. All right, number 9. Is it possible to use the formula? Wait, I was like, wait, what about number 8? I just looked at that 7. Is it possible to use the formula P, A, and B equals P, hold on, P, A, and B equals probability of A times probability of B given A? That's for a dependent case. When events are independent, explain your reasoning. Well, we don't use it in this case, but if we have an independent event, probability of B given A means the same thing as probability of B. They say explain your reasoning, but so here's the idea. Probability of B given A is the same as probability of B during independent event. During independent event. This is because A is not affecting B's outcome. In an independent event, A doesn't affect B's outcome. B given A says probability that B occurs given that A occurs. Who cares if A occurs in an independent event or not? B is still going to be the same probability regardless. It's only in a dependent event where it changes. So what was the question? Is it possible to use the formula? Yes. Yes, because in an independent event, in an independent event or trial or whatever, probability of A and B equals probability of A times probability of B. So yes, you can substitute that. Like I said, probability of B given A is also probability of B in that situation. So yes, 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 yes. All right, number 10. Let's go in order. According to a survey, about 58% of families sit down for a family dinner at least 4 times per week. You ask 5 randomly chosen families whether they have a family dinner at least 4 times per week. Draw a histogram of the binomial for the survey. Binomial distribution for the survey. So this is one where I might have to do some pausing in between, but let's see. You ask 5 randomly chosen families. So N is 5. That's the 5 trials. Probability of success is 58%. The 4 times per week, we're not actually using that number 4. That's just the category for, it's like how many of you eat chicken or whatever. It's just the category there. Q is the 1 minus 0.58, that's 0.42. 58% chance that they do, 42% chance that they don't. So what I'm going to do is, in terms of drawing the histogram, you know, we have a formula that we use here. Probability K equals, we're going to do 0, 1, 2, 3, 4, 5. I'm going to pause this and speed it up in a bit. So what I'm going to do here, guys, there's a whole formula thing that we do. In this case here, we do N choose K times P to the K power times Q, the 1 minus P to the N minus K power, like that. And we're going to be doing those here. So this one will be 5 choose 0 times 0.58 to the 0 power times 0.42 to the 5th power, and so on and so forth. I'm going to not do those for the other ones. I'm just going to kind of get it filled out from my calculator, and I hope that that's okay as we work those ones out. So let me pause it just in case there's a recording mishap. Okay, so I filled this thing out. So I didn't write out the other formula parts. I kind of just used for my calculator. I got them from here using my own version of what I can use in a binom PDF scenario. So got those ones filled out, got them written out. Now we got to go to the histogram portion. And who knows, maybe I have to build this one with you. I think it's okay. I think we'll be good time-wise if I kind of get things done in this level. So here we're going up to, what's the highest percentage? 30-something%. So I'll make sure to do multiples of 5. So we'll go 5%, 10, 15, 20, 25, and 30. For this is probability of K, and K is the different 0 through 5. So 0, 1, 2, 3, 4, 5. Now these numbers are on my calculator still, so I'm going to go ahead and just pull them from there. So on my calculator, let's see, I got a fill color, line color, thickness. Okay, so I'm going to fill up kind of bar graph things here. First we start with 1.3%, which is very minimal. About like that, really small, really small. And then we go for one family. The whole question was, you know, when you randomly select exactly, what if 0 families said that they spend 4 and more nights at dinner, like dinner time a week or whatever. Exactly 0 families, that's a very small percentage. We have around, oh, I'm sorry, it's not 0.1, oh yeah, that's right, 1.3%, that's right. And then we do about 9% here, okay? And of course, snappy. And then about 25% next is the 0.24 number. If you have them written down, you can, or if you don't have them written down, you can go and write them down. Around 25% there. And then around 34.4% here for 3. That's the highest one. So that's trending toward 35% up there. Might as well just kind of stick it up like that. And then, what do we got next? 0.23, so 23.7%, really close to 25 there. Quite close. And then the last one we have about 6.5%. Oh, you can see it right here, 6.6%. So, yeah, that might show a little high. It's kind of a symmetrical normal curve thing there because the 0.58, right? Now, what are some questions they have after that? That was part A, draw the histogram. Part B, what is the most likely outcome of the survey? So here's part A. Part B, most likely outcome is 3 families. 3 families will say that they sit down for family dinner at least 4 times per week. 3 families stating they sit down for dinner at least 4 times per week is the most likely outcome. All right. Part C, what is the probability at least 3 families have a family dinner 4 times per week? So at least 3 is 3 or more. Probability that K is greater than or equal to 3. We're looking at probability of 3. It should say K equals 3. Let's see. Probability that K equals 3 plus probability that K equals 4 plus probability that K equals 5. So in that case, we got to add those 3 sets together. 0.344, 0.238, and 0.066. 0.344, 0.238, and 0.066. Now, these were rounded. These were rounded values, so I'm going to kind of do my best calculator version of this to make it happen the way it's supposed to. So give me 1 second there. 5.8 and 2. I think this is right. This looks like this should be right. So we're going to be around 0.647. I feel like there would be a slight rounding, or 64.7%. I feel like there's a slight rounding error, at least to the nearest 1/10 of a percent there, if we did it a little differently. And I think that's going to be the best version that we can do. So I'm going to leave it at that. Let's move on to number 11. You are choosing a cell phone company to sign. Let's move forward. You're choosing a cell phone company to sign with for the next 2 years. The 3 plans you consider are equally priced. You ask several of your neighbors whether they're satisfied with their current cell phone company. The table shows the results according to the survey. Which company should you choose? So with this thing here, you really want to look at conditional probabilities of all the companies themselves. You want to find what's the probability that they were satisfied. Probability they were satisfied given that you were with a certain company, given company A, and satisfied given that you were with B and C as well. These ones will be the important comparison. Not how many people were satisfied, because you can say, oh, 10 people were satisfied. But what if 100 were dissatisfied, right? So A, B, C. So satisfied given A, there are 4 that were satisfied in A out of 6 people total, which is 2/3, which is around 0.667. Now, the next one, there are 4 satisfied out of 7 in total, and that's around something. I think it's around 0.57. Let's see. 4 divided by 7. 0.571. 0.571. And then the next one, satisfied in C, there's 6 out of 11, the 6 plus 5. 6 out of 11, I think, is even smaller. 0.545. So even though there were more satisfied with company C, there were also more people that we're talking about. It means more dissatisfied. So which should you choose based on this? I mean, all of them are pretty small sample sizes, but company A has the highest satisfaction rate. Therefore, I will choose company A. I would honestly do a lot more review stuff. I'd be doing a lot more reading. That's not very many people to be asking around. All right, number 12. Out of 10,500 people that attend a math conference, 7,315 people are either college professors or female. There are 4,680 college professors and 5,140 females. What's the probability a randomly selected person is both a college professor and female? So let's let event A be college professor, event B be female. A, college prof, B, female. Okay, so probability of A or B is either or 7,315 out of 10,500. Now, I'll leave these as these fractions for now. I'm not going to reduce anything because the addition and subtraction stuff I have to do later. Probability of A, I mean, listen, everything's dividing out of 10,500, so it's just that. We can divide at the end if that helps. But probabilities are still what we're writing. Probability as a college professor is 4680 over 10.5. And then probability of B, female, is 5140 out of the 10.5. And probability of A and B is unknown. So there's some overlap, obviously. There's some overlap. So we're going to say 7315 over 10,500 equals, we got 4680 plus 5140 minus this probability of A and B. This is a case where you have something that's not mutually exclusive. There are indeed females that are college professors. So we are, there's a lot of work to be had in terms of writing this. 4680 plus 5140. This gives 9,820. So if you do some things, I'm going to add probability of A and B over. I'm going to subtract 7315 over. I still have 9820 from these two added here. And I'll subtract the 7315. Eventually, yeah, I'll write the decimal version or a reduced fraction. Let's now do subtraction. 7315 is 2,505. 2505 over 10,500. Now, when I divide this by 10,500, I get a pretty wonky decimal. Let's see if there's a fraction equivalent to this that's reduced a little bit. So the fraction reduction version is 167 over 700. Now, there's a decimal equivalent as well. If I write it as a percentage, it's about 23.86%. And I don't know how deep we can get into that, but about that large of a percent is both a female college professor. Female college professor from that set. There's the overlap, and we had things considered. All right, number 13. Consider a bag that contains all the chess pieces in a set as shown in the diagram. That is a proper amount of everything, indeed. They should have a surplus, of course, in case some are lost. A. You choose one piece at random. Find the probability you choose a black piece or a queen. First of all, I don't know what the extra column's for. We'll see. But maybe totals. But you choose one piece at random. Find the probability you choose a black piece or a queen. Now, there's overlap here, right? Probability of black or queen. I'll just do that. Probability of black or queen. I'll do lowercase for the colors. Probability of black plus probability of queen minus probability of black and queen. There is a black queen in there. So, probability of black, that's half of them, right? You know what? Here, let's do the totals. It should be 16, right? 2 plus, yes, 16 here, 16 here. Okay. Probability of black is 16 out of 32. Probability of queen is 2 out of 32. And black queen, there's 1 that we take out. So black or queen, because otherwise we're doubling that up. That'll give you 17 out of 32. Now 17 out of 32, really close to 50%, a little more. 17 out of 32 is 0.53125. So as an exact value, 53.125%. Boom, boom. That is part A. Part B, you choose one piece at random, do not replace it, then choose a second piece at random, find the probability you choose a king, then a pawn. Now there are, so probability of king, capital, then P. These are dependent events, it depends on what you choose first. First, there are 2 out of 32 that are kings, and there are a total of 16 pawns. Now, if I don't replace it, that means there are only 31 pieces left to choose from. Remember, the 2 out of 32 is you're still just selecting one piece. You're not selecting both. So selecting one of them and then this afterward. So in terms of reduction, 16 out of 32 is 1/2 and 2 out of 2 is just 1. So you're left with 1 out of 31. The probability of making that happen is 1 out of 31. And 1 out of 31 as a percentage is about 3.23%. Like that. So 1 out of 31 or 3.23%. And that, ladies and gentlemen, is the end of number 13. And the last question from the chapter test that we have is number 14. And then we'll go on to the cumulative assessment for 10 more questions. So number 14, please no histograms, please no histograms. 3 volunteers are chosen at random from a group of 12 to help at summer camp. What's the probability that you, your brother, and your friend are chosen? So this is an order doesn't matter thing, whether it's you, your brother, etc. So it's just us as the one thing. So probability of us chosen is going to be, I'll just say 3, choose 3, which is 1 out of, and then here, 12 choose 3, right? 12 people to choose from, and we'll select 3 out of that set. So 12 choose 3, I'm going to let my calculator do this. 12 choose 3 is 220. So we have a 1 out of 220 shot of letting this happen. Please, oh please let this happen. There's some people that are like, I really don't want to be selected with them. The only one I'd want to do it. And imagine this was the thing that happened. No. The first person chosen will be a counselor. Second person will be a lifeguard. And the third will be a cook. What's the probability? You're the cook, your brother's the lifeguard, and your friend's the counselor. Now order matters because the first person chosen, whatever that order matters. So it's still, there's only one possibility that this happens, literally specifically with that, right? That's 1 for that out of, but it's no longer 12 choose 3. It's 12 pick 3. Now when order matters, this arrangement's going to be significantly more massive as a whole. It's going to be in the thousands, I assume. So now 12 pick 3, 12 pick 3 is 1320. So suddenly this becomes 1 out of 1320. Yeah, that's very little chance. I would not bank on those chances there, guys. Definitely not. All right. So y'all, that is it for the chapter test. As long as I can get the next 10 questions done in about 40 minutes, I'm good. So 4 minutes of problem, I am game. Let's go ahead and move forward to the cumulative assessment, shall we? And with that, here we go. So, number 1, according to a survey, 63% of Americans consider themselves sports fans. That is low. Come on. You randomly select 14 Americans to survey. Draw a histogram. Oh, that's a big histogram. Okay, I'm going to have to do some pauses with this. But draw a histogram of the binomial distribution of your survey. Okay, here's probably what I'm going to intend on doing. I'm going to create a table where I need 2 columns and 15 rows. I need 15 rows because I need to... Where'd it go? It's down here. Because I need to have x and p of x at the very tippy top. No. How do I kind of, there we go. I need to take this whole thing. I need to bring it. This is the part where I really should be pausing. This is the part where I'm not so certain I'm going to get this done in a certain amount of time anymore. Okay. So let me kind of fill this thing out. Oh boy. Oh boy. Sorry, I'm trying to shrink the font size here. All right. Let me fill this thing out for a little bit. Hold on. So we'll do... Oh, I need one more row because I need 0. Insert row. There we go. All right. 0. The only problem is you're not going to see everything at once with myself in the picture, and I can't really edit it, so it's not going to show me in the picture. So just kind of fall in some trust here that everything's going to go out the way they're supposed to. All right, so what I'm going to do here... Well, actually, I can probably shrink it some, because I'm probably going to type the values. Can you see that? Yeah, there we go. All right, so I'm going to do... They didn't tell us to fill out a table. I'm doing that out of the kindness of my heart. I need you to see the numbers, though. So I'm going to go to here. I'm going to set up a binom PDF of, what do they say? 63% of Americans. So 14 selected, 63.63%. And then this X as the wild child of chosen values. So I'm going to have to write out all these values here, which look like they'll be incredibly small. I don't know what the purpose is of having some numbers so small here. The highest being 21% in the middle, and then we go from there. So let me fill these ones out, and I will get back to you. Wow, that number's small. It might as well be 0. Hold on. Okay, thanks to my formula and calculator, I typed these ones out. So now I have to make the histogram, another part where I could probably just as well like pause it and work on it a little bit. I'm definitely going to just make it taller like this one so I can fit as much as possible for the sake of the thing, but this is going to be it's going to be crazy. So yeah, definitely got to fit a lot here. Let's see, if the highest is 21%, 2, 4, 6, 8, 10. Maybe we can go all the way to just 20 right here and just kind of fit, because I want to fit as much as I can, because a lot of them are like under 0%. I want to fit those that I can make that. I put that top one as like 0. It literally is just whatever. And I'm only going to write this as 20% and 10%. I think we can figure out the rest from there. But this part, this is going to be small. Hold on. 1, 2. All right, let's see. Let me first fit these in. 0, 1, 2, 3. All right, did the best I could. Okay, so with that in mind, wow, this is going to be quite the shrinkage here. So 0 is basically at 0%. Nothing else I can do from that. It's very, very small. So is 1 and even 2. Remember, these aren't really percentages, though. They're decimal equivalents. That's still 0.02%. I mean, this is going to be 2% right here. I don't know if I'm going to fit 0.02%. Even 0.01%, these are just so small, they are insignificant. 0.01%, I'll pretend like I tried to draw something, and you can't even see it. You can't even see it. I don't even think it registered as a thing. So at 0.07% is something that I can... Well, actually, what did I say this was? 0.016%. Okay, if this is 2% here, maybe I can get a smidgen bit of an appearance of it like that. After that, it's just, 1% is in between this right here. Let me kind of fit these just so I have them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. And I'm slowing down on this because it's a strategy thing for you drawing it as well. These are kind of interesting and big things. This isn't a test. It's testing me, all right. 1%, 0.7%, then might be around there. And then we hit 2.5%. So there's 2. Here's 2.5. Abouts. I just hate that thing snaps. I'm going to have to just live with it if it does that snap. 6.6% about. Getting its way near 7. And then 12.8%. So 10, 11, 12. There's 12.8, sure. And then 19.12. It's kind of fizzling out a little bit. Actually, no, it's not. 19 is way up here. 19. That's not fizzling. That's dominating. About 19-ish% there. And then we hit our 21. So I'm just scroll up a little bit. I know you can't see it, but let's see. We'll go here and then 21 probably be about up there. So pretty high up. Sorry that we can't get it all in one snapshot. 18.5-ish. So 18, 16, 17, 18.5-ish. And then 11.4. This looks like a histogram, all right. It's a beauty. Okay. 4.87, so around 5%. Just a smidge under. Wouldn't even be able to tell. 1.2%. A little more than 1. And then last one is 0.1%. 0.1% is like that one from before. Really probably can't tell as a whole. Just kind of leave it there. It kind of exists. Just barely. All right, there's our histogram. Don't even see the top. There it is. All right, what's the, was that it? Draw a histogram. What is the most likely number of Americans who consider themselves sports fans? If you randomly select it, so 9. 9 is most likely outcome. 9 most likely outcome. That's part B, actually. Outcome. Okay. Part C, what is the probability at least 7 Americans consider themselves sports fans? So probability that this thing is greater than or equal to 7. It says at least 7. So we're going to have to do quite a few things here, but I'm just going to P of 7. Probability of 7, 8, 9, 10, 11, 12, 13, and 14. So they're asking quite a bit here. I have a quick way of doing this in my calculator, but you're taking these ones and adding them together. So if you'd like to go ahead and try and type that in, you can. I have kind of a quick way of making that happen, like I said, and I'm going to go ahead and give that a shot right now. So let's see if I can do this. We're timing each other, right? So you start in your thing, and I'll time myself. 14.63, and I'm getting, okay, I'm done. I'm getting 89.88%. So 0.89876, etc. So 89.88% within that set, sports fans. We good, we done, we taken care of. So that's what I'm getting there. That's what I'm feeling. Hope you're feeling the same thing. Hope that's what you got when you added them up. So that's number 1. So averaging 4 minutes a problem, well, that was more than it. Number 2, not a stats-based question. Place each function into one of the 3 categories. So no zeros, 1 0, or 2 zeros. This is quadratic-based things. We got to take a look at one at a time. And honestly, what we can do, if I can determine it's factorable, that would definitely mean 2 zeros. But I think for these, let's just work off the discriminant if I can't tell if it's factorable. Here I can't tell. It doesn't. I don't think it's factorable. So let's just try it. B squared minus 4AC is 16 minus 24, which is negative 8. That means no zeros. I'll make sure to copy and paste the table at the very end after this. So there's that one. No zeros for this. Let me just put a 0 next to it. Okay. Next one, f of x equals negative x squared plus 2x. I can tell you now that that's factorable. You can factor a negative x out and you get x minus 2. So x is 0 or 2. And in that factorization, that means 2 zeros. So 2 zeros. On the next problem, we got f of x equals 4x squared minus 8x plus 4. I can factor a 4 out, and I get x squared minus 2x plus 1. This is a perfect square trinomial. By the way, this is when things equal 0 that happens. I know I didn't write that. But this is x minus 1 quantity squared, which means x equals 1 is the only solution to that thing. That's 1, 0. 1, 0, haha. And that goes there. And then next one, f of x equals x squared minus 3x minus 21. I don't know any factorization for that, so let's try the discriminant of it. We get b squared minus 4ac. Now the good news, not good news, but the sign that I can see here is that although it's not a perfect square discriminant, it is still positive. That means there are still 2 zeros. It's just not factorable in that way to present the 2 zeros. It's not rational solutions, but there are still 2 of them. F of x equals 7x squared. The only solution when you set that equal to 0 is that x equals 0. That's just 1 0 that comes out of that. The vertex is right on the origin for that one. And then the last one, f of x equals negative 6x squared minus 5. If I set this equal to 0 and I'll get rid of the negatives, but I'm about to subtract, I get 6x squared equals negative 5. You can tell that here you're going to get a no zeros case because you have something where you're taking the square root of a negative. So I'm sorry, this one wasn't no zeros on this. This was 1 0. But that's no zeros there. So if we're going to copy and paste this thing and write the things in, I'm going to have to do it on the other page, but at least I have the numbers written on the other side. So let's go to that. Let's copy and paste it as we continue on problem number 2. So a lot of things done at once. I know I did them relatively fast. They are based off old material though, so it's something that's kind of more so expected as we're testing it. So first one I can write is 3x squared plus 4x plus 2, and then negative 6x squared minus 5. The next one, or on 1, 0, you have 4x squared minus 8x plus 4 and 7x squared. And then for the last set, you have negative x squared plus 2x. It's always assuring to get 2 of them in each of them. At least I can fit them. X squared minus 3x minus 21. Although they were irrational zeros, it still worked itself out. And that's your final solution for number 2. Was it under 4 minutes? I have no idea. Number 3. Surely some of these must be faster. You order a fruit smoothie made with 2 liquid ingredients and 3 fruit ingredients from the menu shown. How many different fruit smoothies can you order? So this should be faster. Liquids, I got 1, 2, 3, 4, 5, 6 combination or 6 different possibilities, and I can choose 2 of them. Order should not matter for here. And then 1, 2, 3, 4, 5, 6, 10 fruit ingredients, and I'm going to be able to choose 3 of them. So I'm going to do 6 choose 2 times 10 choose 3. Now 6 choose 2. 6 choose, whoopsie, not logic. 6 choose 2 is 15. So I'm going to do 15 times and 10 choose 3. 10 choose 3 is 120. So 15 times 120, what is that, 1800? Equals, I'm going to assume it's 1800. Let's say times 15. 1800. So 1800 different, wow, this place, and that's in order, doesn't matter. This place will never go out of business. That's a lot of different fruit smoothies you can order, my guy. That was a quick one. Number 4, select all the numbers that are in the range of the function shown. Range is representing the y values. So we got piecewise function. This would have been from chapter 1. So x squared plus 4x plus 7 if x is less than or equal to negative 1, and 1/2 x plus 2 if x is greater than negative 1. This is one of those things where I don't want to make this like a multiple selection thing where I try them and see which ones work. I'd rather just try and kind of graph it and go from there. So I'm going to use graph paper for this. I do have those always on hand, handily available. So I got this guy right here. Let's go ahead and graph. So I'll go ahead and attach graph paper for you guys. Let's start with the bottom one, this 1/2 x plus 2. Now, plus 2 is right here, and it's a slope of up 1 over 2, like this. Now, they say this applies for all x's that are greater than negative 1. So negative 1 is right here, and when x is greater than is where we apply this thing. So that one over there is not going to count. I'll make sure to erase it, but I'll make sure to draw this linear function like that the rest of the way. So there's that. Part of the piecewise function. I can't get rid of that 1 point. There we go. All right. The green one I'm going to do right here. Let's start with getting the vertex. The vertex value for x is negative b over 2a, which is negative 4 over 2, or negative 2. The y value for that is going to be negative 2 squared plus 4 times negative 2 plus 7. That's 4 minus 8, which is negative 4 plus 7, which is 3. So the vertex is at negative 2, 3. I'm going to have to obviously move all this work because I'm going to be drawing something here. So there's all that work. Negative 2, 3. 1, 2, 3 is right here. This goes until x is less than or equal to negative 1. This is a stretch factor of 1. So 1, 1, and we hit that, and we're done on that side. And then we go left. 1, 1, 2, 4. And that's kind of all I can plot right there. So this graph does this, and it goes up forever. They're asking about range. What values exist in the range? The lowest value that we hit, and we don't actually technically hit it, is... so our range is basically y is greater than 3/2. How do they say it? 1.5. Y is greater than 1.5 is our range. We don't hit that, but we hit everything above. We hit 2 and 3 and everything above there as it goes up. We hit nothing below. So which values are included in this thing? Nothing here, but all these are yeses. These are all part of the range of the function, the piecewise function. Okay, let's go to number 5. Complete the equation. So the solutions of the system of equations are negative 2, 4, and 1, negative 5. Well, the bottom portion of the equation I couldn't care less about. If those are indeed solutions, then they work out. Great. I only care about the top one. I have some y equals mx plus b, and I need to go through -2, 4, and 1, -5. There are a lot of ways we can go about this. There's a classic way of finding the slope and y-intercept, whatever. We can plug it in as a system and solve. I don't really know which one's best for this kind of thing. I was really thinking of it like a system here. But let's just do the m stuff. Slope is rise over run, y2 minus y1 over x2 minus x1. I'm trying to think of what section this would belong to, though. I know where we did system stuff, but I'm not going to try and solve it in like a wonky way. If I can get the slope and y-intercept, I'm going to. So my slope's going to be -3. So now my equation looks like y equals -3x plus b. And I need to go through either of these 2 points. Let's plug in this one here. Let's plug in 4 for y and -2 for x. So this is 6. Hold on, let's do that again. Plus b. So 4 equals 6 plus b. Therefore, b is -2. So the equation there is going to be y equals -3x minus 2. That's the one that will go through those 2 points. And apparently the bottom equation also satisfies that. There's no way to dance around what we have on that other set. That is what it is. So I'm going to have to leave it like that. I don't know what the bottom part's for at all. Number 6. Use the diagram to explain why the equation is true. Probability of A plus probability of B is probability of A or B plus probability of A and B. Well, the general case of these equations is probability of A or B. And if I subtracted probability of A and B from both sides, I'd get this. Probability of B, whoopsie, that's a weird looking B. Probability of B minus probability of A and B. So I subtracted A and B from both sides. So after rewriting equation, we get the known formula for for overlapping events in an OR case. And the diagram shows an overlapping event. That's why this will be okay. That's it for number 6, and that was another statistics question, so I'm going to move forward to number 7. Which polynomial represents the product of 2x minus 4 and x squared plus 6x minus 2? So let's check it out. 2x minus 4 times x squared plus 6x minus 2. Let's distribute. We're going to multiply 2x into all 3 of these guys here, and we get 2x squared, or 2x cubed, excuse me. 2x cubed plus 12x squared minus 4x. And then on the bottom, -4 distributes into these. -4 times x squared, -4 times 6x, and -4 times -2. When we combine things, we got 12x squared minus 4x squared, -4x minus 24x, and the 8, and that's the result. So which one matches 2x cubed plus 8x squared minus 28x plus 8? B. B. And I don't know which ones you might end up getting a mistake, like, oh, this is how you would have gotten this answer. I'm not sure. Number 8, a survey. I already feel like I want to copy and paste this. A survey asked male and female students about whether they prefer to take gym class or choir. The table shows the results of the survey. So let's check it out. We're going to fill out this two-way table. I'm sure that's what part A is asking. Part A, complete the two-way table. Yes. So we'll find totals that we can work out, like 50 plus 56 here. 23 plus what is 56? Well, 33. 49 minus 33 is 16. Subtract that, you get 34. And 34 plus 23 is 57. 57 plus 49 indeed equals 106. So I think everything indeed lines up the way it's supposed to. There's our two-way table completed. Part B, what's the probability a randomly selected student is female and prefers choir? So female and prefers choir is the 33 out of the 106. Probability female and choir is 33 out of 106. Going to be close to 30%. We'll go and see what that is in just a moment. 106. 33 divided by 106. I'm getting 31.1%, or 13%. I'll just go ahead and get to that number. So boom or boom, right? That's called the joint relative frequency for that one. Part C, what's the probability a randomly selected male student prefers gym class? Now we're only talking about male students, so we are only referring to this row of values. Now preferring gym, 34 of the males prefer gym, so C, probability of gym given male. We're talking about those 34 out of the 50 males, which is 68%. 68% of those. And as a reduced fraction, by the way, that's 17 out of 25. Like so. So 17 out of 25. Boom, boom. All right. That is number 8. Let's move to number 9. 2 more questions. The owner of a lawn mowing business has 3 mowers. There's a lot of statistics questions within the cumulative assessment. And that's good. It's fine. It's just interesting. Okay. The owner of a lawn mowing business has 3 mowers. As long as one of the mowers is working, the owner can stay productive. One of the mowers is unusable 10% of the time, one is unusable 8% of the time, and one is unusable 18% of the time. Find the probability all 3 mowers are unusable on a given day. So it's one and the other and the other. So probability of all unusable. So that's probability. Do they call them mower A, B, and C? Not really. But what we're doing is if one of them is unusable 10% of the time, we multiply that with probability this one's unusable and this one's unusable and this one's unusable. So we actually multiply all 3 of those together and we get some result. So point times that. I'm getting 0.00144, which is 0.144%. Not only less than 1%, very, very, very small. Near 0% chance, which is good. Find the probability at least one of the mowers is unusable on a given day. So at least one unusable means this is unusable or that one or that one. I think you just add them up. I'm trying to make sure that we're not saying like, oh man, that makes it like a worse off effect that happens, but you still would add up those 3, So, no, let's see. At least one is unusable on a given day. I don't want to just add them up and say this or that, well, yes, I do. I will subtract the result of the overlap. It's just that this isn't a bad thing if all 3 are unusable, or is it? What they say, as long as one is working. So it's kind of just, I don't know. But probability of at least one unusable. Okay, because there's some overlap here, right? Because the and case. So that's going to be 0.10 plus 0.08 plus 0.18 minus all of them being unusable. So 0.00144. At least that's the way that I'm going about that. I don't know if that's right. I'm not really sure that that's how that one works because it's not just all 3. There's a different form of overlap here. And actually, we talked about that overlap before where it's like you actually add this at the end normally. You would actually subtract these 2 being unusable. So these 2 being unusable. And then subtract these 2 being unusable. Hold on, I don't need this number here. And then let me move some stuff over. And then these 2 being unusable. And then you add in that last set. That's the way that I'm going with it. If it doesn't seem like a right-ish value, I'm going to go ahead and keep thinking about it. So the first set of 3, that's 0.36. And then I got to subtract the sum of these ones. I'll do it like this, minus the sum of these ones together. So I got 0.10. And if you don't know what I'm talking about here, I'd have to find the specific problem that we looked at this on. It was more of an enriching kind of question, but I don't know. 0.08 plus 0.1 or times 0.18. Hold on. One little thing is going to mess that up. Plus 0.1 times 0.18. So that's 0.018, I think. So that's going to be 0.0404. I don't really need parentheses. Minus 0.040, geez, 0404. And then plus 0.00144. So if I do all three of those, let's do 0.36 minus 0.0404 plus 0.00144. And I'm getting 0.32104. So I think that's how that one works, 32104, which is 32.104%. So what I did here, once again, was this wasn't just two overlapping circles. It wasn't just this plus this minus the overlap. There are three of them. So what I had to do was, in the ABC case, I first started talking about these three here, 1, 2, 3, but then I took out the overlap of this, this, and that, but then that ended up taking out the whole middle, so I added that in after the fact. So that was, these ones were the green here, these ones were the purple here, and this one was that yellowish one there. And when all told is there, that's what we get. So that's what I'm going with on that part, and I believe that was just a part. Yes, that was part B. So probability on a given day, any of them are, which doesn't take you out of business on the day, but it's still a good probability to talk about if at least one's unused. Suppose the least reliable mower stops working completely. 100% chance it's gone. How does this affect the probability the lawn mowing business can be productive on a given day? To be productive, you need at least one to work. So one to work or the other to work. So the least reliable one is the one that's unusable 18% of the time. Let's get rid of that one. So probability of day, of productive day. So we need at least one to work. So that means for one to work, we need this one to work and the, no, not and the other one to work. We need to make sure that the other two do not work. So find the probability this one doesn't work and the other doesn't work and do 1 minus that. So 1 minus probability of one and the other working. That's what is it? 0.1 times 0.08. Which I believe is 1 minus 0.008, because I think you divide it by 10, so I think that's 0.992. Wait, the other one's completely unproductive. I think that's fine still. So 99.2% chance that you're still going to be in business. Is that right, though? Is that within that number of the thing? Because the other one was 0.144% chance. So yeah, that one's still above it. So how does this affect the probability there? Before it was, I don't know, it's slightly lower because what would have the other one been? 0.144%. 0.144%, and that would be, let me get rid of this sound. Sorry. That one's a reminder that, hold on, I need to change that. That was a reminder that I need to be quicker on the ball with this thing here. Let me disable that completely. My phone's a little wonky right now. Okay, got it. All right. Yeah, the other one would have been, so it would have slightly improved probability. Or it would have slightly decreased the probability. It would have slightly decreased probability because you have less to look forward to still having another one work. The other one would have left you at 1 minus 0.00144. That would have had you at 99.856%. So this other one was at 99.856% there. All right, let's see. Running short on time here, but I only have one more question. Number 10. Write a system of quadratic inequalities whose solutions represented by the graph. Okay. For these ones, I can use vertex form. Oh, no, these aren't vertex form. Hold on. Those are wait. Ooh, I don't know that vertex. Okay, let's start with the red one. The red one, I see a vertex at 1, 5. I see a vertex at 1, 5, and I see that the stretch factor is -1. So I can call this one y is, and it's less than, it's underneath, and it's a dotted line. It's a negative stretch factor, negative x minus 1 quantity squared plus 5. That would be the red one. I'm going to go ahead and darken that a little because I don't like looking at that color red. So let's just get a darker version of that red like that. All right, so there's that one. The blue one, we're going to have to do a little bit more there. I see some intercepts. I see an intercept here and here. This one is at negative 2, 0, and this one is at 3, 0. We don't have to write it in vertex form. In fact, I can write them both in standard form later if you want me to. So this one is y is greater than or equal to, there's some a times x plus 2 times x minus 3. We're going to have to find the a by plugging in an xy value. We have 0, negative 6, negative 6 for y, 0 for x. I'm putting it as equals temporarily here because we got to solve for a first. So negative 6 is negative 6 times a, so a is 1. So this is the inequality y is greater than or equal to 1 times x plus 2 times x minus 3. So in standard form, this one here is going to be y is greater than or equal to x squared minus x minus 6. And then this other one is going to be y is less than, I got negative x squared minus 2x plus 1 when expanded, and plus 5. And then distribute the negative, negative x squared plus 2x minus 1 plus 5. And then that becomes y is less than negative x squared plus 2x plus 4. And it does hit at 0, 4. And this one does hit at 0, negative 6, so that's an agreement. So those are both in standard form. I don't know if it mattered which form we actually had. Here was first factored or intercept form for this guy. Here was vertex form for this guy. And then I just went ahead and cleaned up what they had. So there they are. All right, guys, I think I made it in time before the recording stopped on me. So, hey, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. Glad I was able to get it in for you. Let me know if you have any questions. If I rushed too fast, check the description section down below for more. So, guys, thank you. Take care. I will see you in the next one.